This presentation offers a review of the bonding and structure ideas that were introduced earlier this year in the Elements of Life topic. We're going to be thinking soon about intermolecular bonding, and there won't be any point doing that if we can't decide when that will occur. So we need to be able to decide, is something a molecular substance? Does it have covalent bonding with molecular structure? Or does that not apply at all? Does it have a different form of bonding and structure? So we're just going to have a look again and make sure that we're happy with making that decision. What is the type of bonding and structure in a substance? You need to be able to decide from the formula of a substance whether it is ionic, metallic, covalent, network, or covalent molecular. So for instance, if I was just to give the symbol Cu, that stands for copper, and you should be able to look at that and think, okay, that's metallic bonding because it's just a metal, and therefore it'll have a metallic lattice structure. If I was to put down the substance SiO2, silicon dioxide, looking at the elements in that, they're non-metals. So we think non-metal only, covalent bonding. That leaves the choice of giant network structure or simple molecular structure. Now in this case, you're supposed to remember that for silicon dioxide and the element carbon on its own, or the element silicon on its own, it's the covalent bonding with the giant network structure. If I was to write down NaCl, we can look at that and say, okay, there is the metal sodium, the non-metal chlorine. Metal and non-metal together gives us ionic bonding, and that has the giant lattice structure. If I was to write down C2H6O, which could be ethanol, we look at that, we see there's only non-metals present, which means covalent bonding, and again that gives us the choice, is it covalent with the giant network structure, or is it covalent with the simple molecular structure? In this case, it's not one of our few ones that do the giant network structure, so like most covalently bonded things, it will be the simple molecular structure. And that's the situation we'll be considering shortly when we come to talk about intermolecular bonding. Intermolecular bonding only applies where you have molecules, because you have covalent bonding with the simple molecular structure. We'll just think for a minute about these various types of bonding and structure. When you have ionic bonding, so we said that's metals and non-metals, you need to be able to draw the dot cross diagrams, and you see those on the right here for lithium oxide and magnesium fluoride. Remember, with those, what you do is you put the two separate types of ion in square brackets. You put the charges for each ion at the top right hand corner, and you do the dot and cross diagrams around the non-metal, showing its own electrons plus the number it's gained to get up to the stable 8. For the metal, you don't have to draw any electrons around it because it'll have lost its outer shell electrons in the process of the bonding. You also need a balancing number in front of the square brackets if there is more than one of that particular ion in the formula of the compound. You also need to be able to represent one layer of the structure for an ionic substance, and if you remember, for a simple one-to-one ionic substance, you get the kind of diagram shown on the left with the alternating positive and negative ions. The negative ones are drawn bigger than the positive ones, and if you're talking about a particular substance, you must of course label that with the formula of each of the positive and negative ions. With metals, we get this kind of lattice of positive ions. So those are drawn regularly arranged in neat rows and columns, and then in between them we get these delocalized electrons. Remember, with a metal, the outer shell electrons delocalize and move around between the positive ions, and it's the opposite charges attracting there that hold the structure together. Again, if you're talking about a particular metal, rather than just having the positive sign in the ions in the lattice, you want to label it with the actual symbol and charge for that metal. So for instance, magnesium, being in group 2, loses its 2 outer shell electrons, they delocalize, and so we would draw the Mg2+ ions. Moving on to non-metals, if we look at the option where you have the giant network structure for covalent bonding, we get these kind of extended ongoing networks. Now if you remember, you don't actually need to draw the structure there or do dot cross diagrams particularly. You do just need to remember the specific cases: silicon dioxide, the element carbon on its own, and the element silicon on its own. Finally, the thing that's going to be of interest to us in the coming lessons, covalent bonding with a simple molecular structure. So this is where you have non-metals and it's not the silicon dioxide, carbon as an element, or silicon as an element. Carbon dioxide then is a perfectly good example where you have a molecular structure, and if we think of that in the context of air, then we can see how when you've got molecular substances, then you have all these separate molecules. There's bonding within the molecule, holding the atoms together, the covalent bonds, but between different molecules, so in the air around you now, the molecules floating around separately, there's quite limited attraction. There aren't any of the bonds we've discussed so far, ionic, covalent, or metallic, and that explains why those ones are gases at room temperature. However, there must be some attraction possible between the molecules, because if we start to cool air to very low temperatures, the molecules will come together in the liquid state, and they wouldn't do that if there wasn't some attraction. So it's that we'll be looking at as we move on to the intermolecular bonding topic. So we'll leave you with one question to think about that you should be able to answer from this presentation. For each of the following substances, what would the type of bonding be present between the atoms, and what would the structure be that results from it? So first of all, iron oxide, Fe2O3. Secondly, carbon in the form of graphite. Thirdly, ethane, the 2-carbon alkane C2H6. And fourthly, tungsten. Make sure you've got the answer to those ready for when this material is discussed in class.